Alright, this is chapter 1 homework for Physics 101. The first is just for significant figures. Carry out the following operations. The sum of the measured values 756 plus 37.2 plus 0.83 plus 2.5. Now if we put this in our calculator, we get a 796.53. But when we're adding numbers, we keep the lowest number of decimal places. So here 756 has no decimal places, so the answer is rounding properly 797. Part B, the product 0.0032 times 356.3. If I calculate this, I get 1.1402. But when I multiply numbers, I keep the lowest number of significant figures. This number only has two significant figures, so the answer is 1.1. In part C, the product of 5.620 times pi. Pi has a numeric value of 3.14159, da 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 da. Pi is a pure number, so it has, you don't consider it when you're considering the significant figures. Now if I put this into my calculator, I get 17.6558, and it goes on, maybe for infinity. And I keep the lowest number of sig figs, which is this. It only has 4, so the answer is 17.66. And in part D, it's a mixed operation of 3.42 times 25.4, 25.4 divided by 3.2 plus 2.32. I want to keep my sig figs, my significant figures, as I go along, but I'm going to follow the order of operations. So the first thing I'm going to do is do this multiplication. Then I'll do the division, and then I'll add the numbers. And at each step, I keep the correct number of significant figures. So the first one gives me 86.9. When I do this multiplication, 3.42 times 25.4, the lowest number of sig figs has 3, so I keep 3 significant figures, divided by 3.2 plus 2.32. Now I do this operation, and I get 27, keeping the lowest number of sig figs, which is 3.2, only has 2, plus 2.32. And when I do that, I get 29.32, but I keep the lowest number of decimal places, so my answer is 29. The population density of Los Angeles is about 4,000 people per kilometer squared. That of San Francisco is about 6,000 people per kilometer squared. How many times further away is the average person's nearest neighbor in LA than in San Francisco? So this is really just sort of to help you think about numbers and units and what have you. So if I look at LA, for each person, there are 4,000 people per kilometer squared. So for each person, there is an area of 1 over 4,000 kilometers squared. So if you want to think about this in units, you can think of it as 1 over 4,000 kilometers squared per person. So each person has that amount of area. And then likewise, in San Francisco, each person has an area of 1 over 6,000 kilometers squared. So that's 1 over 6,000 kilometers squared per person. That's their space, if you will. So I want to know how far apart are these. Now I know that area, if I'm looking at a square, is equal to L squared, if that square has a length side L. So L then is equal to the square root of area. So I can just find out what is the distance of L for LA and for San Francisco. So for LA, I'll call it L sub LA, is equal to the square root of 1 over 4,000. That's the square root of the area and that gives me 0.016 kilometers, which is equal to 16 meters. So in Los Angeles, each person, if you were to spread all the people out evenly, they'd be about 16 meters from the next person. Now, for San Francisco, I'll call this LSF. It's equal to the square root of 1 over 6,000. And that's equal to 0.013 kilometers, or 13 meters. So in San Francisco, each person is separated by about 13 meters. So San Francisco is a little more densely populated. Alright, so they'd stand 3 meters closer. And it wanted to know how many times farther away is the average person's nearest neighbor in LA than in San Francisco. So I just say LA over L for San Francisco. That's equal to 16 meters over 13 meters, and that's equal to 1.2. So in San Francisco, they are 1.2 times, or excuse me, in Los Angeles, they are 1.2 times farther away than if they were in San Francisco. So that's the answer. A house is 50 foot by 26 foot and has 8 foot high ceilings. What is the volume of the interior of the house in cubic meters and in cubic centimeters? So first, my volume is 50 by 26 by 8. Alright, keeping the proper number of sig figs, I should only have 2 sig figs, so that is 10,000 cubic feet. Now I want to convert this into meters, and the conversion factor, which I will always provide for you, 1 meter is equal to 3.28 feet. 1 meter is 3.28 feet. Again, I'll provide that to you. So I want to convert this into cubic meters and then cubic centimeters. So I say 10,000 feet cubed Oh, by the way, up here, this came out, if I put in my calculator, like 10,400 feet cubed. But because I kept 2 sig figs, I didn't keep the 4, so I just kept the 1 and the 0. So in this case, when I have the 10,000 right here, it looks like it only has 1 significant figure, but the 0 is actually significant because of just the way I rounded, or because of the way the number was. So anyway, 10,000 cubic feet. I do 1 meter over 3.28 feet. Alright, but I want to get rid of the cubic feet, so I have to cube this term, so that gives me that. And I say 10,000 divided by 3.28 cubed. And that is, I get 283. 283, which keeping 2 significant figures is just 280 cubic meters. And then I want to convert that 280 cubic meters into cubic centimeters. So in 1 centimeter, there are 10 to the minus 2 meters. Remember, this comes about from the metric prefixes that you're responsible for. That is that N is nano, is 10 to the minus 9. Mu is micro, that's 10 to the minus 6. M is milli, that's 10 to the minus 3. C is centi, that's 10 to the minus 2. And then we go to the other side. K is kilo, that's 10 to the 3rd. M is mega, that's 10 to the 6th. And then capital G is giga, and that's 10 to the 9th. Right, so those are the metric prefixes. We see that centi is 10 to the minus 2. So 1 centimeter is 10 to the minus 2 meters. We have to cube this to make this cancel out with this, leaving us with cubic meters. And so that is 2.8 times 10 to the 8. 2.8 times 10 to the 8, and that's in cubic centimeters. So these are the answers: cubic meters and cubic centimeters. By the way, another way of doing this second one, or another way of thinking about it, and this is usually the way that I think about it, 280 cubic meters I know that in 1 meter there are 100 centimeters, and hopefully you'll get sort of know this as well. And then it's just a little easier for me to do the numbers in this way. So it's 2.8 times 10 to the 8 cubic centimeters. Whatever you choose to do is fine. Alright, for the triangle shown in this figure, what are the length of the unknown side? I want to know what is the length of that side, what is the angle theta, the sine of the angle phi, and the tangent of the angle theta. When you're working through these, and this will primarily become important when you're doing vectors, you need to remember your definitions for sine, cosine, and tangent. Of course, there's the mnemonic SOH, CAHTOA. That's SOHCAHTOA. There's also a variety of other mnemonics that you can use to remember this. Right? There's also the Pythagorean theorem, which says that the sum of the squares of the legs, that is a squared plus b squared, is equal to the hypotenuse squared. Right? So for part A, I want to know what x is. That's one of the legs, so I say x squared plus 6 squared is equal to 9 squared. Let's see, I should have 3 sig figs for each of these. And so if I solve for this, it's the square root of 9 squared minus 6 squared, which is equal to 6.71 meters. So this is equal to 6.71 meters. Now, for part B, I want to know what is the angle theta. I can find theta in a number of ways. I know that the sine of theta, SOHCAHTOA, S-O-H, is opposite over hypotenuse. That the sine of the angle theta is opposite over hypotenuse. The opposite of this angle theta is this side. So that's equal to 6 over 9. So if I solve then for theta, it's the inverse sine of 6 over 9, which gives me an angle for theta of 41.8 degrees. Part C, I want to know what is the sine of the angle phi. So now I don't want to know the angle phi, I just want to know what is the sine. It's opposite over hypotenuse. The opposite of phi is 6.71. The hypotenuse, of course, is 9. And that gives me 0.746. There are no units on that. There are no units for the trigonometric functions. By the way, this gives you the angle phi. If you do the inverse sine of 0.746, phi works out to be 48.2 degrees. And then finally in part D, I want to know what is the tangent of the angle theta. SOHCAHTOA, tangent is opposite over adjacent. Opposite over adjacent. The angle theta, the opposite side is the 6 meter side. The adjacent side is the 6.71 meter side. And that gives me 0.894. And again, if you want to find theta, which you often will in this course, it's the inverse tangent of 0.894. Which is 41.8. Oh, we've already found it. It's 41.8 degrees. Yeah, it's the same as what we found up here, but just a different way to find that angle. Estimate the number of ping pong balls that would fit into a typical size room without being crushed. In your solution, state the quantities you measure or estimate the values you take for them. Okay, this is a useful skill, and you'll see it on the exam. That is to be able to estimate things, their distances or their masses, or their areas or their volumes, in terms of the metric system. So the first thing you want to do is consider a room, and you want to estimate roughly how big it is. How big is it? I'm going to take a 9 by 9 by 9 room, because that's roughly what my office is. 9 by 9 by 9 room. That's 9 feet, by the way. And 9 feet, 9 by 9 by 9, that's roughly 3 meters. So this is also 9 feet is approximately 3 meters. So the volume, the approximate volume of this is 3 times 3 times 3, which is 27 cubic meters. I could round that off to 30, but I'll just keep it at 27. And now I'm going to assume my ping pong ball. You know, a ping pong ball is a sphere, but if you stack spheres, they actually stack like cubes. So I'm going to assume my ping pong ball to be a cube. Alright, and that ping pong ball is going to be approximately 3 centimeters. 3 centimeters, that's like half my pinky, almost. And so that's approximately the diameter of a ping pong ball. And so I'm going to consider the volume of the ping pong ball to be, or the stacking volume, if you will, of the ping pong ball to be 3 by 3 by 3 centimeters. 3 by 3 by 3 centimeters, which is 27 cubic centimeters. So now I want to convert this now to cubic meters. So I know in 1 meter there are 100 centimeters. I have to cube that. So that tells me that there are 2.7 times 10 to the minus 5 cubic meters in a 3 by 3 cubic centimeter, or 3 by 3 by 3 centimeter cube. So now if I want to know how many of these will fit into this, then I just divide their volumes. I say 27 cubic meters divided by 2.7 times 10 to the minus 5 cubic meters. That's equal to 1 times 10 to the 6 ping pong balls. So I can fit 1 million ping pong balls into my office, stacking them all the way up to the ceiling. 1 million ping pong balls. Which I've never done, but if you could, that's what you could fit. So you should have a rough idea of what is a centimeter, what is a meter, what is a kilogram, and be able to estimate the area, volume, what have you, of various things for the exam. What is the volume of your body in cubic centimeters? Alright? Describe how you estimate this volume. There are a couple different ways. You can treat your body, kind of look sort of like the Tin Man, as cylinders. This is a rough approximation of your body. You have cylinders with a sphere, no feet, no hands, just the major appendages, cylinders and a sphere. Alright, you can treat it like that and determine the volume of each object, and that's okay. That's an approximation, but I'm going to make it even a more general approximation. I'm going to say that my body is basically a cylinder. Alright, my case, I'm about 6 foot tall, so the height of this cylinder from my toes to my head is about 2 meters, a little under, but I'm just estimating, so it doesn't really matter. I'm going to say that my radius, that is from here to here, is approximately 30 centimeters. That's 0.3 meters. That's approximately right. It's about 30 centimeters from the center of my chest to my shoulder, to the edge of my shoulder. And then I want to calculate the volume of this approximated body. The volume is pi r squared times h. That's the volume of a cylinder. In general, I'll expect you to know the basic equations for volume, like for a cube, for the area of a square, what have you, the area of a triangle. But they don't come up that often. Alright, so this is equal to pi times 0.3 meters squared times 2 meters, and so the volume of my body is approximately a half a cubic meter, or 0.6 cubic meters, give or take, a couple of tenths of a cubic meter. Analyze the dimensions for each of these equations. Are they dimensionally correct? Alright, you don't not necessarily know the units of each of these, so M has units of kilograms, that's mass. V and V naught both have units of meters per second. Be careful that you don't confuse the variable m with the unit m. A and G both have units of meters per second squared, and X and h are both measurements of length, and so they both have units of meters, or m. Now, when you're testing whether an equation is dimensionally correct, you want to put the dimensions in place of the variables, and likewise you just leave all the, or not likewise, but you also just leave off all the constants. So for example here, I'm just not going to worry about these halves because they don't affect the dimensions of the overall equation. I just want to see if the dimensions match up. M is in kilograms, V is in meters per second, but it's squared, so I'm going to go ahead and square both sides. That's equal to M is in kilograms, V0 is in meters per second, but it's squared. So you see, so far these units match up, and that's plus the square root of kilograms meters per second squared times meters. Now this part right here is going to simplify to the square root of kilograms times meters over seconds. But this is not the same units as this or this. So this is not dimensionally correct. Let's look at this one. X is in meters, M is in kilograms, A is in meters per second squared. M is in kilograms, V is in meters per second. That's both squared. If I rewrite these, I get kilogram meters squared per second squared is equal to kilogram meters squared per second squared. That one checks out. So if you have an equation and you're not sure if it's correct or not, you can just put the units in and see if the units work out. And if they work out, then it's likely that you have the equation correct. Unless, of course, if you don't have these constants in the right place. Alright, this other one, M meters per second is V. Meters per second is V0. V0 is an initial velocity. The 0 down here basically means at time equals 0. We'll see that in the next chapter. Plus meters per second squared. Time is in seconds. I didn't write that over here, but time is in seconds. So these seconds squared cancel. So I'm left with meters per second, but then just meters over here. So this one is not dimensionally correct.